All right, Abel, we're changing our mind a little bit. We just got to in chapter 6, and we're going to dabble a little bit in chapter 10. We got 2 sections to do in chapter 10, and then we're going to review for chapters 10 and 6, and then we'll do semester review and all the things. So 10.5, I'll give you this when you come back, but 10.5, vectors in the plane. All right, you guys had vectors in physics. What is your prior knowledge of vectors in physics?
Direction and magnitude.
Magnitude and direction.
60 miles per hour north.
Okay, magnitude and direction. Okay, magnitude and direction. Magnitude is the how much, right?
Yeah, how quick?
Okay, so like what did you just say?
60 miles per hour.
60 miles per hour. That's a magnitude. Okay, the direction is
Where it's going.
where it's going. So like 42 degrees north of east, right? That would be a direction. Okay? Got it? Magnitude, direction, vectors in the plane. All right. So this vector, just FYI, like if I draw this vector would look like this. Boop. 42 degrees and 60 miles per hour. Okay, that's what he would look like. All right. Now, ready?
You can add and subtract vectors.
Now, you can add and subtract vectors. Okay? Yeah, kind of. You might like vectors, okay? So, here's the deal. Vectors are a lot of times written in what's called component form. Okay, we'll deal with a couple different forms. There's component form and there's polar form, okay? So, component form is like written with like little triangular brackets, right? So, if I want to represent this vector with component form, what I have to do is I want to figure out how many units he's going in the horizontal, which is the x direction, and how many units he's going in the vertical, which is the y direction, right? How do I do that if I'm given this information?
Triangle.
Yeah, like sine and cosine, right? Okay, so let's talk about just x first. Let's say I want to find the x direction. So this guy right here, right? Okay, I have 42 degrees and I have 60 miles per hour. 42, this is a right triangle, by the way, so I can use SOHCAHTOA, right? 42 degrees, what is x in relationship to 42?
Adjacent.
The adjacent, what's 60? The hypotenuse. So which trig function are you going to use?
Cosine.
Cosine, and we're going to do cosine because it's CAH, right? Cosine of what?
Uh-oh.
It's not. It keeps threatening that it's going to shut off and it won't.
Cosine of 42.
Cosine of 42 equals, the adjacent goes first, so it is x over 60, right? Okay, if I multiply the 60 over 44.6, we'll say, miles in this direction, right? Okay, now I want to figure out how many miles it is in the y direction, so up from there, right? Like if I'm trying to get, like let's say like a ball that I'm throwing, right? Starts here at the origin and I throw it at 60 miles per hour, 42 degrees from the horizontal, and it ends here, right? Before it drops down, right? Okay, how far does it travel horizontally? We just figured that out, 44.6. How far will it travel vertically? We're going to figure that out, right? So that is using, because this is opposite in hypotenuse now, so we have sine of 42 equals the opposite, which is y over 60. So I multiply the 60 over,
40.1.
and that's 40.1 degree, or 40.1 miles, I guess is what it is, right? Each one of those is in miles. So it's gone 44.6 miles in one direction, 40.1 miles in the other direction, right? Okay, so this is like not realistic for a ball that I'm throwing, but anyway. Okay, so that's how that works, right? So vectors are a lot of times written in component form, which is this guy. Now, you want your vectors to be in component form in order to be able to add them together. So for example, let's say this is a ball that I'm throwing, right? Okay, what does that oftentimes encounter when I'm like throwing something or tossing something? Wind resistance. So we have another vector that is acting against it, okay, that is wind. And maybe that is 120 degrees at, let's say we have a 10 mile per hour breeze, right? Like that is going to affect the change of the vector, right? Or like where the ball ends up. So I can figure out if I have this vector and this vector together, I would have to convert this vector into component form, right? But then I could add them together, right? That's like how that works, okay? Yes, all right. That is way more detailed than what we're going to get into today. Today we're just talking about component form and like what vectors look like. So a vector will have an initial point, and an ending point. And it will have an arrow so you know which one is which, right? It starts and ends. So initial point and a terminal point. So starting at P, ending at Q. Got it? Okay. Vectors are denoted with bold-faced letters like U and V and W, right? So like vector U, they write it like this. Vector W, they write it like this. Vector V, they write it like this, right? I don't know. That's just how they do vectors. It's kind of like R, like all reals, whatever has a boldface R. Vectors are written with lowercase letters, and they are written with like a little bolded area, right? Okay. So UVW, U is this small vector that is going straight upward, whatever. V is going kind of more in the downward position, but it's a long vector. So that might be going like 100 miles an hour, right? Instead of 60. So usually the way that this works is whatever the magnitude is, the bigger the magnitude, the longer the vector is how we represent that, okay? So this might be going 100 miles per hour versus this one is going like 30 miles per hour, right? 30 miles per hour straight up. This one's going down and to the right, like kind of in the fourth quadrant. This one might be going like 80 miles per hour, right? And it's going upward mostly, okay? So magnitude, direction, each one of these kind of has a different direction, and the magnitude is reflected by how long the vector is. Got it? Okay? All right, magnitude is denoted, circle this guy, with like, they put him in kind of like absolute value brackets, right? So like if I'm talking about the magnitude, like how long the vector is, I want to use these two little absolute value brackets, and that tells me that I'm trying to find the magnitude, okay? Now, vectors are only equivalent if they have the same magnitude, so this is the same length, and they're going exactly the same direction. So, are these two equivalent? Yes, they are going the same direction and they have the same magnitude. Are these two equivalent? Why not? They have the same magnitude, right here, same magnitude, different direction. They're going opposite ways, right? What about this guy? No, they are same direction, right? They have the same slope, but they are different magnitudes. And then these two guys are neither. They don't have this, they have different directions and different magnitudes, so those are not the same. So the only ones that are the same are the first ones. Got it? Magnitude, direction, same thing. All right, here we go. Example 1. They want us to confirm equivalent vectors. Confirm equivalent vectors. Show that those two vectors are the same. All right, so let's talk magnitude for just a second, okay? So if we're doing PQ, we're trying to find the magnitude. Let's just do magnitude of PQ. Put that down. And then we're going to do magnitude of, that should be OR, not QR. There's a typo right there. OR. Magnitude of OR. So we're going to find the magnitude of each one of these. Magnitude is how long it is, right? So if they give me where it starts and they give me where it ends, how do I figure out how long that thing is? Yeah, I do the distance formula, right? Okay, distance formula is this guy squared plus this guy squared. Do you remember distance formula? Yeah. How far apart is 1 and 5? 4. How far apart is 2 and 4? 2. Okay, 4 squared is 16. 2 squared is 4. This guy has a magnitude of the square root of 20. Okay, and so how they will write that is they will write like this, P, Q, with the two little lines in it, right? That's magnitude. Okay, so the square root of 20 is the magnitude. All right, I'm going to do the same thing for the other one. If we're doing OR, how far apart is 0 and 4? 4. How far apart is 0 and 2? 2. Okay. 4 squared is 16. 2 squared is 4. That's the square root of 20. So the magnitude of OR is also the square root of 20. Now, these vectors, we don't know that they're equal yet because the magnitude checks out, but let's talk direction. Okay, so we're going to do direction of PQ, and we're going to do direction of OR. Okay, how do I judge their direction?
Based off of coordinates, like where they start.
Yeah, where they start and where they end. So that is having to do with the what?
Slope.
The slope, right? Okay, so let's find the slope from P to Q, and then let's find the slope from O to R. Okay, so if we, how do we do slope, by the way?
y1 minus y2.
Y2 minus Y1 over X2 minus X1, right? Okay, so if I'm looking at PQ, I got to zoom out a little bit. What is the second Y coordinate on PQ? Second Y coordinate on PQ.
2. No.
4 minus 2 over 5 minus 1. 4 minus 2 over 5 minus 1. 4 minus 2 is 2. 5 minus 1 is 4. So the slope is 2 over 4 or 1/2, right? That's my slope. That's my direction for now. Like we'll get into direction needing to be in a degree measure later, but he is going up 1 and over 2 units, okay? Actually up 2 and over 4 units. Okay, this guy, OR, is starting at, if I go y2 minus y1, 2 minus, oh, I just got rid of some stuff. 2 minus 0 over 4 minus 2. 2 minus 0 over 4 minus 2 is also 2 over 4, which has a direction of 1/2. So he is going the same direction for the same amount. He is going the same direction. He is going the same magnitude. What?
4 minus 2 isn't 4.
It should be 4 minus 0.
Oh, that should be 4 minus 0, sorry. Thanks for catching that. Yeah, I wrote it wrong.
You should just like teach physics next year.
Yeah?
Yeah, you should just like teach
You think so?
physics next year.
Okay.
Yeah.
So the magnitudes check out. They are the same length of vector. Their directions, their slopes check out. They are going the same direction. So I have this going on. I have this is the square root of 20 and this is the square root of 20. And he is going up 1 and over 2 and he is going up 1 and over 2. So are those vectors equal to each other? Yes. Okay. Now, it could have been that the square root of 20 and the square root of 20, we checked those, right? But we can't stop there because one of them could be going a positive 1/2 and one of them could be going a negative 1/2, right? So we have to check both of them, and that's the important part, right? They both have to check out. The magnitude has to be the same, which is the distance formula. The direction has to be the same, which is the slope formula. Got it? Okay. All right, so this one, I don't know why they had to do example 1 before example 2, because we really needed to do this one first. But it says find components and magnitude of a vector. So they want components. What's component form again?
The triangles.
The little triangle brackets, okay? So how far he's going in each direction. All right, so component form. If I'm starting at -2 and I'm going to 4, how many units have I gone in the x direction? I've gone 6, right? If I'm starting at 6 and I'm going to -3, how far have I gone in the y direction? I've gone down 9. That's my component form, right? Okay, now, yeah, right. Then they ask for magnitude. Magnitude is how far, right? That is the distance formula, right? Okay, so if I do the distance formula, all right, check this out. How far apart is -2 and 4? 6. How far apart is 6 and -3? 9. Oh, hey, look at that. It's just the component form basically put into the distance formula, right? Okay, except you don't need the negative on the 9. Like, you can put it on there if you want to. It doesn't matter, right? So this is 36. This is 81. 36 plus 81 is 117. And the square root of 117, I think they might actually give you it, have you do it as a decimal. What is it? What's the square root of 117? 10 point, what?
8.
10.8? So 10.8 units, it might be miles, whatever. And this is the component form. So it's going to the right 6 and down 9. Okay, so component form. And then this is the magnitude. Got it? Yeah, not too bad, not too bad. All right, should we stop there?
Yes.
We'll stop there. If you want to do some homework, you can do 1 through 4. If you want. Whatever. Okay, all right, there we go.